life part. Life part. All right.
Now, the title of my talk is General Relativity, a Case Study in Numerology. Now, I mean that both facetiously and literally, because I'm going to show you today, using mathematics and numbers, that general relativity and all its associated things such as black holes and big bangs are really nothing other than some kind of numerology. I'd like to dedicate my talk today to these three late musicians, John Lord from the rock group Deep Purple, and these two men, Huey Thomason Jr. and Billy Jones, from the southern rock band, The Outlaws. Some of you, as old as me or older, will certainly remember them. The first thing I'd like to do is to begin by baking a cake. Now, what kind of a cake it is a cosmological cake. The first thing is a bit of a recap before I go into mathematics of all of this, is things that I've spoken of in the past by comparing the characteristics of black hole universes to Big Bang universes and seeing simply the very simple underlying contradictions that make them impossible. Now, the first thing is black hole universes are spatially infinite. There are three types of Big Bang universes, one spatially finite and the other two are spatially infinite, depending on their K curvature values. The black hole universe is eternal. That means it's static. It doesn't depend on time. Whereas Big Bang universes are all finite in age. They're 13.8 billion. I believe that they've now raised it to 13.9 by tweaking a few knobs. Now, the black hole universe is, by definition, something that only contains one mass. Well, that doesn't really correspond to what we see in the sky. I see at least two, and I'm sure you see more than two. Now, Big Bang universes allegedly contain as many masses as you like and radiation. All black hole universes are not expanding. As I mentioned, they're static. But all Big Bang universes are non-static. All black hole universes are asymptotically flat. Some really esoteric types are asymptotically curved, according to the cosmologists, but we won't be talking about any of them today. They're not worth it. But no Big Bang universe is asymptotically anything. Finally, all black hole universes, or no black hole universes, have a K curvature. And we've already seen that all Big Bang universes have a K curvature, one of three different values. So you see, you cannot put black hole universes into Big Bang universes, or vice versa. But what do the cosmologists do? They mix the two willy-nilly and get millions of black holes, billions of black holes. NASA's found 2.5 billion of them. The ESA just found one a couple of days ago in the Milky Way, not at the center, but revolving with another star. So they've got a binary black hole system. And all of this, of course, in a Big Bang universe. Which one, they don't tell us. They never tell which black hole either, because there are four types, you might recall from a previous talk that I gave. Black holes have a very schizophrenic property. Right? They have and do not have an escape velocity simultaneously at the same place. Now, no cosmologist understands what escape velocity means. I've mentioned this in detail in my previous talk, but this is a recap today. So that's a problem. Nothing has an escape velocity and no escape velocity simultaneous at the same place. But that's exactly what the black hole event horizon has. In fact, they tell us at the black hole event horizon, the escape velocity or the escape speed of a black hole at the event horizon is the speed of light. That's why nothing can escape. Really? If light is traveling at the speed of light and that's the escape speed, wouldn't you expect light to escape? I would. Let's continue. X is a black hole universe and Y is a Big Bang universe. X plus Y is not a universe. Neither is X plus X or Y plus Y. Why? Because general relativity is a nonlinear theory. You can't just add these together like solutions in simple equations and add them together. You can't do that because it's a nonlinear theory. Here's a simple graphics example of black holes. According to general relativity, or the cosmologist, every black hole has infinite curvature at its singularity. Well, if it has infinite curvature at every singularity, that's gravity. Gravity is not a force in general relativity, it's space-time curvature. So they're telling us that at each one of these black holes, see them in that little drawing there, each one of them has infinite curvature at its center, its so-called singularity. However, does any one of those have asymptotic flatness? Well, you go from one black hole to another one, and what do you encounter? Infinite gravity. You go from another one to another one, infinite gravity. Every black hole encounters infinite gravity at every other black hole. That's not asymptotically anything, and that violates the definition of a black hole universe. It's supposed to be asymptotically flat at the very least, so it's nonsense. Now we get into a little bit of mathematics. We're up to baking a cake 4.1. Whose cake are we baking? Well, the cosmologist's cake and Einstein's cake, and I think they'd really like to have a file in it somewhere. General relativity, well, these are the equations of Einstein. Now, all you really need to do here is to identify parts. G, what's that? This big G thing? It's Einstein, the Einstein tensor. The R thing there with the arrow there, R sub UV, this is the Ricci tensor. R on its own is derived from the Ricci tensor, and it's called the Ricci scalar. And G, this is an important thing called the metric tensor. It's sometimes called the fundamental tensor. We'll talk about metrics. And lambda is the cosmological constant. And T is the energy momentum tensor. That's it. We've identified all the parts. But what do they mean? Well, the energy momentum tensor is supposed to describe all the material sources of Einstein's gravitational field, and the G is supposed to describe the geometry, because matter causes space-time to curve. So the matter's on the right side, making the space-time geometry on the left side curve. That's gravity, according to Einstein. And the cosmological constant, what is that? Cosmologists don't really know. Einstein didn't really know. It's a fudge factor. Here's an interesting thing. Static and in the absence of matter. According to Einstein, when the energy momentum tensor, which we saw in the previous slide, is 0, his equation is reduced to this thing. The Ricci tensor equals 0. Well, according to Einstein, this describes a gravitational field of a body, or outside a body, such as a star. But this is circular reasoning. First, he removes all matter by setting the energy momentum tensor to 0. There are no material sources. Then, by going in a circle, he comes back and says, this describes a gravitational field outside a body. He just put it back in. That's right. Now, some people will object to that. Oh, Crothers doesn't know what he's talking about. He's not on the wrong trail. Well, really, here we can now prove the argument is circular. Because we take de Sitter's universe, it's described by this second equation, R equals lambda G. Well, according to the cosmologists and Einstein, this universe is empty. It's de Sitter's empty universe, right? It's empty because it doesn't contain anything. Why doesn't it contain anything? Because the energy momentum tensor is 0, just like the one beforehand. So according to Einstein and his followers, matter is both present and absent by the very same mathematical constraint. Do you think that's possible? I don't. It's not possible. So R, or the Ricci tensor equals 0, that universe, if it's a universe, it's as empty as de Sitter's universe for the very same reason. There are no material sources present. It's a contradiction. So that really bakes Einstein's cake completely. I'll have more to say on this later, because that means that setting the Ricci tensor to 0 is physically meaningless. It has nothing to do with physics. Now we come to a little bit of numerology. This is the so-called Schwarzschild solution, but it's Hilbert's version, and it's a magic trick by Hilbert. In this expression, C equals G equals 1. What's C? It's the speed of light. G is Newton's gravitational constant. And they set them to 1, so they disappear out of the equations. And they claim that this little m in this equation is the mass of the gravity that's the source of the gravitational field that Einstein says Rick equals 0 to. This is the mysterious mass that is taken out and put back in. Let's see how they insinuate Newton into this expression. Let's put C and G in explicitly. Now, Hilbert's expression becomes this. C and G are now present, because if you make C and G 1, we get Hilbert's 2m over r. And notice that they want r to go down to 0. This gives them their two so-called singularities. One, they say they can remove the event horizon of their black hole, because when r is equal to this so-called Schwarzschild radius, they call it a radius, and they give it a value, 2gm over c squared. Again, if G and C are 1, you have r equals 2m. And if you put that into that expression there, you find that the second term with the power to the minus 1 becomes 1 over 0. Right? Well, that's undefined, and they call that the event horizon. Then they put in r equals 0, because they want r to go down to 0. They think it's the radius. And they put in 0, and then the first term gets what? 1 over 0 as well. Now notice, if we rearrange this so-called Schwarzschild equation, or Schwarzschild radius rather, for C, we get C equals the square root of 2gm over r. Well, we recognise that immediately as Newton's expression for escape speed. The thing about this, of course, is that Newton's expression for escape speed pertains to two bodies. You have to have at least two bodies because one escapes from another one. Just because one mass is missing from this equation doesn't mean it's not implicitly present. Because if you have two things, one escapes from the other. And this describes what speed is the necessary minimum for one body to escape from another body when the body that you're referring to has mass m. So by this expression, they have two things: a radius of the event horizon of a black hole, and two, the escape speed of the black hole. That's why they tell you that the escape speed at the event horizon is the speed of light. They got it from Newton's expression. How can you put a two-body relation in what's allegedly a solution to a one-body problem? You can't. Here's some further confusion. This is what I call scientific or delusional science. All right? Delusional science. Cosmologists in confusion. What do they think Hilbert's R is? We saw that expression. I've given a list here. They think it's the areal radius, the coordinate radius, the radius. A guy with a Nobel Prize called Gerardus Tuft tells us this. It's the radius. He tells us also it's the distance, so do many others. He tells us it's the radial coordinate, so do many others. It's the radius of a two-sphere, the reduced circumference, the radial space coordinate. And here's my favourite one of all. A gauge choice, it defines the coordinate R. You know? I could call this Fred Flintstone, or I could call it dark matter, or I could call it doesn't matter. It doesn't matter. Because all of them are wrong. Now we'll come to a little bit of surface theory to see why their mathematics is so false. This is a simple expression. It's called the first fundamental quadratic form for a surface. Now the g's, they're functions of two variables, u and v. U and v are the only variables, and you see here that we have a number of terms, GUU, GUV, GVV. Well, GUV is equal to GVU, so that's why it appears twice. But how many variables are there? Two, because it's a surface. Surfaces have only two variables, two dimensions. The area from Gauss's surface theory is given by, or an element of area is given by the second expression. This is an element of area. You would have to integrate that to get the full area over the range for the domain for values of u and v as required. Now, if u and v are functions of another parameter, we'll call it t. But just because I call it t doesn't mean it's time. I could put in Fred Flintstone. U is a function of Fred Flintstone. I could stick it in there, and then I get now an element of length. Anywhere in the surface, I can calculate length between 2 points in that surface by this parameterized expression. T is the parameter. It doesn't matter what you call it, it's just a dummy variable. Metric tensors. This is a lot of things that cosmologists hide behind. Most of them don't even understand it. They say, oh, well, that's a tensor. Really? Well, what's a tensor? Most of them don't even know that. But they use it nonetheless. We want to now calculate a thing called Gaussian curvature, because this will identify what R is in Hilbert's metric. And then we'll see whether or not it can go down to zero. I'm going to show you that it can't go down to zero. And because of that, everything about black holes is immediately destroyed. What's the real radius in Hilbert's metric? We make a calculation. We integrate the term that contains dr. And then we get this expression by evaluating the constant. I put the constant in, and we get the square root of alpha in the second term. Now, notice something about here. When r equals alpha, and in the case of Hilbert, he assigns alpha to gm over c squared, and then he makes c and g 1. Well, rp is 0. That's the radius. So that means when r equals alpha, or 2gm over c squared in the case of Hilbert, this equation is 0. The radial distance is 0. So that means that's where the origin of this geometry is located, and there is no possibility for r going less than 0. Well, r squared is r is a real number, and you square the real number, you get another real number. But the difference is, this squared real number is always greater than or equal to 0. Can r squared take minus alpha? Can r squared be minus alpha? It cannot. Now, since this expression generates Schwarzschild solution, Droste solution, Brillouin solution, any number of solutions you like, and they're all equivalent, if any one of that infinite equivalence class can be extendable to make Hilbert's black hole, in other words, to make Droste's solution go down to 0, then every single one of them must be on account of equivalence. Alternatively, or conversely, if any one of those cannot be made to go down to RC equals 0, capital RC equals 0, then none can on account of equivalence. Well, if I make, you look at this one, can r squared take values of minus alpha and make RC sub 0 0? It cannot. So we don't need homeomorphisms, we don't need diffeomorphisms, we don't need Hausdorff spaces, we don't need topological spaces. This completely ruins the black hole with its simple mathematics. You cannot, because it's an equivalence class. On account of this one being inextendable, none of them can be. So the black hole is a fallacy. It's nothing other than a generation of irrational imagination coupled with nonsensical mathematics that has no relation to physics, because Einstein's field equations R, Ricci, or R sub u v equals naught have no physical meaning. We're going to write Einstein's field equations now in a different form. Einstein wrote them as this. Before it was Ricci tensor equals 0. This is a different form. You see now it's in terms of the Riemann-Christoffel symbols. The left-hand side is geometry, the right-hand side there's no sources, and the square root of the negative of the determinant is 1. Why? Because when you take the determinant of this metric, for example, Schwarzschild's metric, you get -1, you get a negative number, so you have to multiply by -1 to get the square root of a positive number. And Einstein sets up this, what's called a unimodular situation. Cosmologists will throw at you, oh, this is unimodular coordinates, that's why he did it, so what? Now, Einstein makes a modification to the Riemann-Christoffel symbol because he puts a negative in front of it so he can write the top equation with a plus sign. You have to be careful. You can lose signs when you read Einstein. According to Einstein, from that first equation that I gave you, he does a lot of mumbo-jumbo. He uses a Hamiltonian, and he gets up to this thing here. And he says on the left-hand side, we've got this partial derivative. It's really a divergence thing. And on the right-hand side, or it's a partial derivative thing at this stage. I'll talk about divergences shortly. And in the right-hand side, he says, since there's no matter here, right, and there's energy because the gravitational field has energy, I need energy. So what does he do? He concocts a thing called his pseudotensor. This is this little t with subscript sigma and subscript mu. And t is just a number that you obtain. It's an invariant that you obtain from t superscript sigma and subscript mu by setting sigma equal to mu, as we see down here. T is equal to t with sigma and in both subscript and superscript. It reduces the tensor by 2 values, right? And so a tensor with no superscripts and subscripts is a scalar or an invariant. And Einstein defines his pseudotensor, remembering this is what he uses to describe the energy of his gravitational field. Because even though there's no matter there, no mass, he wants energy because, according to him, matter is everything except his gravitational field. That's an important thing to remember with Einstein. Everything except his gravitational field is matter. Well, his gravitational field has energy. So he concocts this thing and says that's the energy. Then how does he get the material sources in? He simply adds it. He adds now the energy momentum tensor. See, now the little t has got a big T added to it. He took that equation and he expanded it by adding in the source. Now he says this describes his gravitational field with its sources. It doesn't look like the equation that we started before, but it's the same kind of thing, more complicated form. We're going to look at some symbol salads. The top one is a word salad. Do you recognize it? Maybe it's Dutch. Maybe it's double Dutch. You know what? It's nothing. Why? It looks like a sentence. It smells like a sentence. It's got a nice European thing there with so I expanded a little bit with a naught with double dots on it. It's got a full stop and a capital letter and a comma. And it looks like words, but it's drivel. Well, that's word salad, right? Then you look at the one below it. You think, oh, that's marvelous. Einstein wrote that, it's marvelous. You know what? It's just as much mathematical salad as the one before it is word salad. You know, but you can't see that, can you? I'm going to prove it to you. Metrics of 0 class is the theorem. I didn't make it up. Go and see the mathematicians. Metrics of 0 class of any number of variables n are characterized by the necessary and sufficient condition that their Riemann-Christoffel curvature tensor vanishes identically. Now, I've put a note. The Riemann-Christoffel curvature tensor for Einstein space-time does not vanish identically. So we're in this thing. Differential invariance. Theorem 2. Metrics phi of class 0 have no non-zero differential invariance. Metrics of non-zero class have no first-order differential invariance. The invariants greater than 1 are the invariants of phi, the Riemann-Christoffel curvature tensor, and its covariant derivatives. So we've got a definition, we've got a theorem 1 and 2. Now we contract Einstein's pseudotensor. He's treating it like a tensor, so we'll perform a tensor operation on this one, as he does, and we get t, just like he does. So the constant t, or the invariant t rather, has this form. We notice something about it. It's a function of what? The components of the metric tensor. In this time, it's written with superscripts. This is just another way. It's called a contravariant tensor. You can write it as contravariant above, covariant with them all below, or a mixed tensor with superscripts and subscripts. So we just switch them around. The delta thing, that's a Kronecker delta function. That's either 1 or 0. If the superscript is equal to the subscript, then the Kronecker delta gives 1, otherwise it's 0. But you see here, also remember that these Riemann-Christoffel symbols, these gamma things, we saw before that they're functions of the components of the metric tensor and their first derivatives. Well, that means Einstein's t here, his invariant, is a function of the components of the metric tensor and their first derivatives and nothing else. Well, we see by theorem 2 here, they don't exist. So by the method of reductio ad absurdum, we assume that Einstein's pseudotensor makes sense in mathematics. We apply a mathematical procedure to it by contracting it. It produces junk. What do we know about the premise? It's junk. So that means his conservation of energy is rubbish. He can't do that. It's nonsense. The whole thing is nonsense. For all of those who are lost a little bit with the mathematics, we can have a little fun. I've come now to Riga. No, it's not the city Riga. It's for the Rusted Iron Gong Award for spectacular phantasmagoria and gross inanity. And the nominees are Gerardus Tuft, Professor of Physics, Nobel Laureate, Utrecht University, for this gem. When I spoke to him about this, he sent this to me in an email. I have the evidence, so if anybody wants it, I can give it to them. He says, of course, no astronomer in his right mind would claim that R stands for spatial distance. Well, you saw what he called it. He had 5, didn't he? He didn't know what he was talking about. He had 5 of them. 4, at least 4, I think 5. But in his notes on general relativity and his notes on black holes, on his own website, what does he say? Where R naught is the smallest distance of the light ray to the central source. Isn't that a radius? Ordinary stars and planets contain matter. T sub UV does not equal naught. Yeah, material sources. With a certain radius, R greater than 2m. Here C and G is 1. He's using Hilbert's. So that for them, the validity of the Schwarzschild solution stops there. So despite the right-mindedness or the wrong-mindedness of astronomers and astrophysics, Tuft tells us that it's both the distance and a radius as well. And yet he's told us that nobody in their right mind would do that. I wonder what he was smoking at the time. Jos Bland Hawthorne, this is one of my favourites. This guy, he's a professor at the University of Sydney at the Institute for Big Questions. I'm serious. It's not a joke. I didn't make it up. The president is, I think, currently John Webb. He's well known to me, as anybody who's been to my webpage will know. Anyway, the University of New South Wales has this Institute of Big Questions. Bland Hawthorne is there, but he's at the University of Sydney and also the Institute of Astronomy there. He says this on National Australian Television. I know, I watched it and I downloaded it. Some objects are so massive that the escape speed is basically the speed of light and therefore not even light escapes. You know, the journalist sat there like a stunned mullet because he didn't even know what he said. But we know what he said. This is because he's saying that black hole event horizons, well, they have that schizophrenic property of having and not having an escape velocity at the same place. So he's a good candidate. Now we come to our old mate Hawking. He's ubiquitous. He's everywhere, this guy, you know. He's like a Big Bang himself. At the Big Bang itself, the universe is thought to have had 0 size and to have been infinitely hot. Really? It's got no size and it's infinitely hot. Well, what carries the temperature, Steve? You know, don't you think you've got to have something that has a temperature? If you take a solid, what is it? Well, you've got these particles bumping around. You take a liquid, there's particles bumping around. You take a gas, there's particles bumping around. Well, we can go take a plasma, there are particles bumping around. But he's telling us that nothing can have a temperature. Not only that, it's infinite, really. An infinite temperature, that even doesn't even make sense. What can have an infinite temperature? Okay, we go, Clem Prikey. This guy's a good one. Clem Prikey, he's a bicep 2 scientist. You know all about bicep 2? You've heard of it. He's a physicist at the University of Minnesota. Now, these guys are the guys that said, we sampled the universe when it was, we sampled beam mode polarizations in the so-called cosmic microwave background when the universe was, after the universe it lived for only 1/trillionth of a trillionth of a trillionth of a second. Now, this is delusional science again. I wonder where they got their clocks. Probably at CERN, because that's where they make the Large Hadron Colliders. And our final one, good old Larry, God bless him. He's a professor at Arizona State University. I'm surprised he wasn't here today to give me a hard time. It seems quite plausible that our universe may be just one universe in what could be almost an infinite number of universes. Larry said that on National Australian television. I know, I watched it, I downloaded it. Well, we asked Larry, just how close, Larry, did you get to infinite number? Really? You got to it's almost an infinite number. How close do you get? You know, you wonder where these guys went to school. I said it before, we're glad we didn't go there. And so who are the winners? Well, I couldn't decide, so it's a dead heat. They all get the prize, and finally, green grass and high tides. Thank you very much.
Globe life fart. Globe life fart.